You know what's weird? Right now, as you're watching this, you're spinning. Not just you, your chair, your phone, the air around you, the entire planet beneath your feet. We're all spinning at about 1,000 miles per hour, and that's just the beginning. The Earth is spinning around the Sun. The Sun is spinning around the center of our galaxy. The galaxy itself is spinning. Even the atoms in your body are spinning. Everything, everywhere, all the time spinning, spinning, spinning. But here's the really strange part. Nobody made it spin. There's no cosmic motor turning everything. No giant hand giving the universe a push. So why is everything spinning? Where did all this rotation come from? And why hasn't it stopped? This question bothered one of the greatest minds of the 20th century. Richard Feynman loved puzzles like this, simple observations that hide deep truths. And when you dig into why things spin, you uncover one of the most beautiful secrets in all of physics. A secret that connects ballet dancers to collapsing stars, ice skaters to the birth of galaxies, and a simple spinning top to the fundamental laws that govern reality itself. Let me take you on a journey. We're going to start with something you can see right now, and by the end you'll understand a truth about the universe that most people never realize. Ready? Imagine you're holding a ball. You toss it straight up in the air. What happens? It goes up, slows down, stops for a moment, then falls back down. Simple. Now imagine you toss it and give it just a tiny spin as it leaves your hand. What happens? It still goes up and comes down, but now it's also rotating. And here's the kicker, it keeps rotating. It doesn't slow down its spin. It doesn't gradually stop rotating. If there's no air resistance, that ball will spin at exactly the same rate until something stops it. Why? Why doesn't the spin die out like the upward motion does? The upward motion fights gravity and loses. But the spin just keeps going. This is your first clue. Nature has a rule, a law that's almost sacred. Once something starts spinning, it wants to keep spinning forever. Scientists call this the conservation of angular momentum, but forget the fancy name for now. Just remember, spin wants to stay. Think about it like this. You know how hard it is to get something heavy moving, right? If you want to push a car, it takes effort. But once it's rolling, it wants to keep rolling. That's called inertia, the universe's laziness. Things that are moving want to keep moving, things that are still want to stay still. Well, spinning has its own kind of inertia. Once something is spinning, it wants to keep spinning. And the universe is extremely stubborn about this rule. In fact, it's one of the most important rules in all of physics. It's so important that if you could somehow violate it, you'd break the universe. Seriously, now, here's where it gets interesting. Let's say you're sitting on one of those spinning office chairs. You know the kind. You pull your arms and legs in close to your body and start spinning slowly. Someone gives you a push. Now here's the experiment. While you're spinning, suddenly stretch your arms and legs out wide. What happens? You slow down, pull them back in, you speed up again. Wait, what? Why would pulling your arms in make you spin faster? You didn't push against anything. You didn't use a motor. You just changed your shape. How does that make you spin faster? This is where it gets beautiful. Remember that rule, spin wants to stay the same. Well, what actually wants to stay the same isn't just the spinning motion. It's something more specific. It's the combination of how fast you're spinning and how spread out you are. Scientists multiply those two things together and call it angular momentum. And that's what nature refuses to let change. So when you pull your arms in, you're making yourself more compact. You're reducing how spread out you are. But the total spin has to stay the same. So if you're less spread out, you have to spin faster to compensate. It's like the universe is doing math in the background, making sure the equation always balances. This isn't just a fun trick with office chairs. This is how ice skaters do those incredible spins. They start with their arms out, spinning at a moderate speed. Then they pull their arms in tight against their body, and suddenly they're a blur, rotating so fast you can barely see them. They're not using hidden motors. They're using a fundamental law of the universe, and this same law explains something absolutely mind-blowing about space. Picture this. Somewhere out in the cosmos, there's a huge cloud of gas and dust. It's enormous, maybe trillions of miles across. And it's floating in space, just drifting around. Now, this cloud isn't perfectly still. Nothing in space is perfectly still. Maybe it has just the tiniest, almost imperceptible rotation. So slow you'd never notice. So slow that it takes millions of years for the cloud to complete even a fraction of a turn. But then something happens. Maybe the cloud starts to collapse under its own gravity. Maybe it's disturbed by a nearby exploding star. Whatever the cause, it starts to shrink. The gas and dust begin pulling together, getting more and more compact. Now remember our rule. Spin wants to stay the same. As the cloud gets smaller and smaller, more and more compact, what has to happen? It has to spin faster and faster, and faster and faster. What started as a barely rotating cloud, rotating so slowly you couldn't measure it, becomes a rapidly spinning disk. And at the center of that disk, a new star is born, often with planets forming in the disk around it. Our entire solar system formed this way. The Sun, the Earth, Jupiter, all of it, all spinning because a cloud collapsed and the universe refused to let the spin disappear. That's why everything in our solar system spins in roughly the same direction. We all came from the same spinning cloud. We're all following the same ancient rotation that started billions of years ago, before the Earth existed, before the Sun existed, when there was just a cloud drifting in space with the tiniest twist, but it gets even more extreme. Imagine that collapsing cloud isn't just forming a normal star. Imagine it keeps collapsing. The core gets smaller, denser, hotter. Eventually, the star runs out of fuel and collapses catastrophically. The core crushes down to something the size of a city, a neutron star. Remember, as it collapses, it has to spin faster. A star that might have rotated once every month or so becomes something spinning hundreds of times per second. Some neutron stars spin faster than a kitchen blender. Some complete a full rotation in just a few milliseconds. That's a city-sized object with more mass than our Sun, spinning faster than anything you've ever seen on Earth. And the universe didn't violate its rule. The spin was always there. It just got concentrated into something incredibly small. And the only way for nature to keep the books balanced was to make it spin absurdly fast. This happens everywhere. When you see a hurricane forming, it starts as a large, slowly rotating disturbance in the atmosphere. As the air rushes inward toward the low-pressure center, it has to spin faster and faster. The same rule. The same conservation of angular momentum. A Category 5 hurricane and a collapsing star are following the same law of physics. Now, you might be wondering, okay, fine, spin is conserved. But where did the first spin come from? If everything came from the Big Bang, and the Big Bang was just a point, how could it have been spinning? A point can't spin, right? This is one of the deepest questions in cosmology, and here's the fascinating answer. The universe as a whole probably isn't spinning. On the largest scales, when you average over billions of galaxies, there's no net rotation. But here's the thing, the universe doesn't have to be perfectly smooth. In fact, it wasn't. Right after the Big Bang, there were tiny, random fluctuations. Little quantum ripples in the fabric of space and time itself. Some regions had slightly more matter. Some had slightly less. And crucially, some regions had tiny little twists. Microscopic amounts of rotation baked in from quantum randomness at the birth of the universe. As the universe expanded and cooled, those tiny fluctuations grew. Regions with more matter pulled in surrounding matter through gravity, and any region with even the slightest twist, the tiniest rotation, would conserve that rotation as it collapsed. A microscopic twist in the early universe becomes a slowly rotating cloud of gas. That cloud collapses and becomes a rapidly spinning galaxy. Stars form from collapsing regions within that galaxy, each one spinning. Planets form around those stars, also spinning. Every single spinning object in the universe can trace its rotation back to tiny quantum fluctuations in the first fraction of a second after the Big Bang. The fact that you're spinning right now, standing on a rotating planet, is a direct consequence of random quantum events that happened 13.8 billion years ago. Think about that for a second. The rotation of the Earth, the reason we have day and night, the reason hurricanes form, the reason galaxies have their beautiful spiral shapes, all of it goes back to the fundamental quantum fuzziness of the universe in its first moments. We're living inside the consequences of ancient randomness, amplified and conserved by the laws of physics over billions of years. But here's another wild thing. It's not just that spin is conserved. It's that the universe is really, really precise about it. Like absurdly precise. If you could measure the total angular momentum of an isolated system, say, a planet and all its moons, and then come back a billion years later, it would be exactly the same. Not approximately the same, exactly the same, down to levels of precision that boggle the mind. Why is the universe so obsessive about this? Why does it care so much about conserving angular momentum? Well, here's where Feynman's genius comes in. He realized that these conservation laws aren't just random rules the universe decided to follow. They're connected to something deeper, something about the shape and symmetry of space itself. There's a mathematician named Emmy Noether who proved one of the most beautiful theorems in physics. Noether's theorem says that for every symmetry in nature, there's a corresponding conservation law. And for every conservation law, there's a symmetry. What does that mean? Well, the universe looks the same in every direction. There's no special direction in space. North isn't fundamentally different from south. Up isn't fundamentally different from down. This symmetry, this rotational symmetry of the universe, is directly connected to the conservation of angular momentum. In other words, the reason spin is conserved is because the universe doesn't have a preferred orientation. If you could rotate the entire universe 90 degrees, all the laws of physics would work exactly the same way. And because of that deep symmetry, angular momentum must be conserved. It's like the universe is telling us something profound. The laws of physics don't care which way you're facing. And because they don't care, rotation has to be conserved. This connects to something even more mind-bending. You know how we said that spinning things want to keep spinning. Well, there's another weird property spinning objects have. They resist being tilted. If you've ever played with a gyroscope or a spinning top, you've seen this. When it's spinning fast, it's really hard to tip over. It wants to keep its axis pointing in the same direction. This is called gyroscopic stability, and it's why bicycles are easier to balance when they're moving. The wheels act like gyroscopes. But why? Why would spinning make something resist being tilted? The answer is our friend angular momentum again. Remember, angular momentum has a direction, the axis around which something is spinning. And angular momentum is conserved not just in how much there is, but also in what direction it's pointing. So if you try to tilt a spinning object, you're trying to change the direction of its angular momentum. But the universe says no, Angular momentum is conserved. The direction can't just change, so the spinning object resists. It pushes back against your attempt to tilt it. This is how gyroscopes work. This is how we navigate ships and airplanes. This is why spinning satellites can orient themselves in space. They carry spinning wheels inside them, and by changing how fast those wheels spin or which direction they point, the satellite can rotate itself without any thrusters, using nothing but conservation of angular momentum. Even your smartphone uses this. Inside your phone, there are tiny, microscopic gyroscopes that can sense when you tilt or rotate the phone. They're detecting changes in angular momentum at a scale smaller than a grain of sand. And here's something that might blow your mind. The Earth itself is a giant gyroscope. It's spinning, and that spin is remarkably stable. The axis of Earth's rotation points toward the North Star, and it stays pointing in roughly that direction year after year, century after century. Oh, it wobbles a little bit over thousands of years, that's called precession, but for everyday purposes, it's incredibly stable. That stability is why we have consistent seasons. If Earth's axis wobbled chaotically, our climate would be a disaster. Summer and winter would randomly swap. But thanks to the conservation of angular momentum, Earth's rotation is stable, predictable, and has been for billions of years. Now let me tell you about something truly bizarre. We've been talking about spinning objects, things like stars and planets and galaxies. But what about particles? What about the tiniest things in nature? Do atoms spin? Do electrons spin? Here's where things get weird. Yes, particles spin, but they don't spin the way you think. An electron isn't a tiny ball rotating on its axis. If it were, the surface of the electron would have to be moving faster than the speed of light to account for the amount of spin it has. And nothing can move faster than light. So what does it mean for a particle to spin? Honestly, nobody knows exactly. It's one of those quantum properties that doesn't have a perfect everyday analogy. But here's what we do know. Particles have angular momentum. They behave as if they're spinning, and that spin is quantized. It can only come in specific, discrete amounts. An electron always has the same amount of spin, always. You can't make it spin faster or slower. It's a fixed property of being an electron, like its electric charge or its mass. And different particles have different amounts of spin. Some have more, some have less, some have none at all. And here's the kicker. The spin of particles is absolutely fundamental to how the universe works. The entire structure of atoms, the way electrons orbit nuclei, the reason atoms are stable, the reason chemistry works the way it does, all of it depends on the spin of particles. There's a rule called the Pauli exclusion principle. It says that two electrons can't be in the same quantum state at the same time. And same state includes having the same spin. This is why electrons stack up in shells around the nucleus instead of all piling into the lowest energy level. This is why different elements have different chemical properties. This is why you're made of complex molecules instead of just a pile of hydrogen. And it all comes down to spin, quantum spin. A property we can't fully visualize, that doesn't correspond to anything actually rotating in space, but that behaves mathematically like angular momentum and is absolutely conserved. Even in the quantum world, even at scales where our intuition completely fails, the universe still obsessively conserves angular momentum. It's one of the deepest rules in physics. It connects the largest structures in the cosmos to the smallest particles in existence. So let's zoom out one more time. We've gone from office chairs to ice skaters to collapsing gas clouds to neutron stars to the Big Bang itself. We've seen that angular momentum is conserved because of the rotational symmetry of space. We've seen that this conservation law creates spinning galaxies, stable planets, and the very structure of atoms. But there's one more thing I want to tell you. One more place where spin shows up in a way that's both practical and profound. You know those science fiction movies where spaceships create artificial gravity by spinning? That's not fiction. That's real physics. If you're in a rotating spaceship, you feel pushed toward the outer wall, and it feels exactly like gravity. Why? Because of inertia. Remember, things moving in a straight line want to keep moving in a straight line. When you're on a spinning spaceship, your body wants to keep moving straight, but the floor of the spaceship is constantly curving underneath you, pushing you inward to keep you moving in a circle. You feel that push as a force, and if the spaceship is spinning at just the right speed, that force feels exactly like gravity. This is how we might create gravity in space stations or on long missions to Mars. We'd build rotating habitats, and the spin would give us artificial gravity. No fancy technology needed, just conservation of angular momentum and basic physics. And here's the beautiful part. If you built a space station like this, once you got it spinning, it would keep spinning basically forever. There's no air friction in space, no resistance. The station would rotate for years, decades, centuries, using no energy at all, just following the ancient rule that spin wants to stay. So why is everything in the universe spinning? Because spin, once started, is nearly impossible to stop. Because the laws of physics conserve angular momentum with obsessive precision. Because tiny quantum fluctuations in the early universe created microscopic twists that grew into galaxies, stars, and planets. Because the universe has no preferred direction, and that symmetry demands that rotation be conserved. Every spinning object, from a child's top to a spiral galaxy, is obeying the same rule. Every hurricane, every ice skater, every neutron star, every electron in your body, all spinning, all conserving angular momentum, all connected by one of the most fundamental laws in physics. And the truly magical thing, this isn't some obscure fact buried in textbooks. This is something you can feel. Sit in a spinning chair and pull your arms in. Watch an ice skater spin. Look up at the night sky and realize that every point of light is a spinning ball of gas, orbiting other spinning balls of gas, in a spinning galaxy made of billions of spinning stars. You're part of this cosmic dance. Right now, you're standing on a planet spinning at 1,000 miles per hour, orbiting a star at 7,000 miles per hour, in a solar system orbiting the galactic center at 500,000 miles per hour, in a galaxy moving through space at over 1,000,000 miles per hour. And all of it, every bit of that motion, every rotation, every orbit is conserved. It's been conserved for billions of years. It will continue to be conserved for billions more. The universe is spinning, and it will keep spinning, following laws written into the fabric of reality itself. That's what Feynman understood. The universe isn't just a collection of random stuff bouncing around. It's a place with rules, with symmetries, with deep mathematical structure. And when you understand even one of those rules, like the conservation of angular momentum, you start to see the universe differently. You see the connections. The spinning figure skater and the collapsing star aren't separate phenomena. They're the same phenomenon, playing out at different scales, and that's the real answer to why everything spins. Because the universe is lazy and conservative, it doesn't want to waste energy creating new spin or destroying old spin. Once something is rotating, the easiest thing for the universe to do is let it keep rotating. Change is hard. Staying the same is easy. So the universe spins because it's always been spinning, because the laws of physics make it nearly impossible to stop, and because buried in the structure of space and time itself is a rule that says rotation must be conserved. Next time you spin around, next time you watch something rotate, remember, you're witnessing one of the deepest truths about reality. You're seeing a law that governs everything from quantum particles to galaxy clusters. You're seeing the universe doing what it does best, following simple, beautiful, unbreakable rules. And somehow, from those simple rules, from that conservation of angular momentum, we get the complexity and beauty of the spinning cosmos. We get spiral galaxies and planetary systems and stable orbits and the very atoms that make up your body. All because the universe refuses to let spin die. All because rotation, once begun, echoes through space and time forever. That's the mind-boggling truth about why everything spins, and now you know the secret.